that good?
Yes.
Here. So, yeah, thanks very much to the organizers for the invitation. Happy birthday to a very old friend, Ron. And I wanted to talk a bit today about some evolution of work of Ron and Tony and colleagues that is now embarrassingly a number of years ago, right? I think it was in the 90s, I think. So it's sort of models, global models for heterotic theory that had all the right numbers for the phenomenologists, string theory, and with many, continually increasing list of co-authors. We are trying to do an F-theory model where the duality is perfect with the right numbers and global, F-theory global, and the right numbers on the F-theory side, so by duality, the right numbers on the heterotic side. That's the goal of the long title mentioned. So I should first list the co-authors here. And when I say this, so Phil Griffiths can correct me if this is an apocryphal story, but so you and Dennis Sullivan and John Morgan. Did I see John Morgan? No. What? Okay. We're doing rational homotopy theory with Dennis Sullivan and so this collaboration resonates with this apocryphal story, and you were all talking and working in the hall, maybe in Princeton, and the lead passed and said, "Oh, higher massy products vanish," and walked on, and then he was a co-author. Is that a true story? More. Well, we have some of that going with some of these co-authors that are okay. So Dave Morrison, welcome. Just move. Let's see, I've got to get the seat in order. Tony Ponte P comes next, right? Stuart Raby, string theorist in the physics department at Ohio State, and Sakura Schaefer. And so one of the, not the only contribution of one of these co-authors who's in the room, so now you're back. I told a story about you, but you're absence. Anyway, so let's go through. Okay. So we had a previous collaboration in which we were trying to get an F-theory model that had all the right numbers for the phenomenologists. And that was a slightly different set of co-authors, but anyway. And something in that model called vector-like exotics. We don't have, some of you know what vector-like exotics are. Anyway, we had vector-like exotics. And I'm going to say we passed Tony in the hall, but it wasn't quite that way. And Cody said, well, on the heterotic side, the way we got rid of vector-like exotics was we had an elliptic family with a bisection rather than a section. And that was something like Hiomassey product Spanish. Okay. So the subtitle of this talk is The Virtues of the Bisection. So let me get my glasses on so I can see the notes. So I don't know how far I will get with this. I'll try to skip a lot because, but say relevant things. Okay. So over here we have heterotic theory. Is the writing big enough that you could see it in the back? And over here, we have F theory. Over here, we have elliptically fibered Calabi-Yau threefold. Over here, well, let's see, I should have drawn this arrow vertically. All right. This is some Del Pezzo, Fano, some base. And over here, we have Calabi-Yau fourfold elliptically fibered. And over B3, and this B3 is fibered over B2 with P1 fibers. So that the P1's here, this vibration. And the duality is that one of these fibers like this, we make this have parameters and we go to the limit and one of this P1 splits in half. Each of these. And then instead of having a Calabi-Yau, a smooth Calabi-Yau fourfold, this breaks up into, well, this notation is terrible, but D, P, 9, sub 2, union, D, P, 9, sub 1. That is, I have, so dp9, so that's the thing that the physicists like, that's really not a Del Pezzo surface, but it's right on the outer edge. Basically, you take P2 and blow up 9 points on the intersection of two cubics or something like that. Okay, so but they call it Del Pezzo 9. So. And then you go to the Friedman-Morgan-Witten dictionary. Oh, whoops, forgot one thing. And where these intersect, these two DP9 bundles, that's the heterotic, that's where the heterotic theory lives. That's a Calabi-Yau threefold, elliptically fibered. You just split it in half. And these two DP9 bundles, there's a dictionary between DP9 bundles and flat E8 but so these are geometric, and then each one of these gives us a flat along each elliptic fiber E8 structure, E8 bundle structure on our W3. So in some sense, the geometry over here at this sort of first iteration controls. Yeah, everybody who in the room who works on these things, of course, can go to sleep because right, for a while this is all we're going to do. Right. Okay. So there we go. So there's some physics over here. There's a Dirac operator. There's something over here called a Higgs operator. There is, so basically through this, go from geometric dp9 to E8, in some sense we're using geometry here to control the physics over here. And let's see, I wanted to say one more thing. This family that we will construct has a bisection, so not a section. So I guess I should do something like that. And that bisection follows over here to bisection of this family. And then there was another problem. You get the bisection, but for those of you who know what it is, there's a problem getting the bulk spectrum to come out. So there's it. And then there was another one of these passing in the Hall moments, but it was a day last August in Aspen. And these two folks said, the problem with the bulk spectrum is your bisection.
You checked the wrong people.
Say again?
Well, the check marks are.
Oh, sorry. Excuse me. Said, well, the problem is we're going to build our model. We're going to break symmetry with something called the Wilson line. That means take a Z2 action on this side, corresponding Z2 actions on this side. Okay. And we make our bisection downstairs by two sections before we take the quotient, and we have to interchange them. So this other comment was, well, the problem is those two sections. One is the standard section of an elliptic family presented in Weierstrass form or something like that. But the other, as we'll see in a minute, have to kind of construct, quote, a little bit artificially. And so the comment was, well, we're having problems with the bulk spectrum because these two sections upstairs are not on equal footing. So you pick a Weierstrass form, right? You've picked an origin, right? The identity element of the elliptic curve, and that had a predominant place up here, even though we had a second section in this. So the comment was, you've got to put those two sections on equal footing. So what the rest of the talk is going to be about is how we do that and the relative virtues of doing that. Any questions? Probably it's too elementary for a lot of people in the room. And if you're not in this business, especially for people like me, these physics words don't take a long time to mean something. Okay.
Are you starting with a partition that has a bisection, then you make a Jacobian map, and you get a geometry that has one section by construction and one more section?
No, so we've got, this is before we do the Z2 action, okay? We have, the standard identity elements, say if this is in some sort of Weierstrass form, the elliptic family is in some sort of Weierstrass form. And then we have some other section, which this is helping me because it's getting, I was going to do these in a minute anyway, okay? Call that tau, call this the identity section. You have to engineer the quotient so that these two get interchanged. So you have the bisection downstairs, right? It's a connected object, right? That interchanges these two. Okay. Say again?
So you went in a homomorphism that says tau psi. Is that triggered in the base or also moving things in the base?
No, it's also moving things on the base. Again, so I think what I'll do is respond to questions and give this talk in a slightly different order than I had intended. So over here, there's a quintessentially super good object called Sgun. And that's where all the physics is happening. There's matter curves there, and where symmetry gets broken. Yeah, this is total fantasy. I don't know what I'm talking about. Anyway, some explosions happen, blow-ups take place, and we all exist, right? Anyway, okay. So we want S gut downstairs, okay? S gut downstairs is going to be an Enriquez. So we need a fixed point free involution on S gut as part of this thing. So it's definitely not over any base. Is that okay?
Is your B2 P1 times P1? B2. What is B2? Is it
B2, until we get to 3 generations, there's something called, part of the right number is there are 3 families of quarks and leptons, I'm told. So we need 3 generations. We're going to have to engineer B2. Basically, we're going to have to blow up a certain point on B2. So we'll have there'll be a B2 hat here, and we'll have a Hertzebruch F1, not P1 cross P1 down here, and we'll have to make sure the inverse image of that point lies in the S gut when we do the blow up, and so then blow up, of course, its inverse image, and that will be our B3 hat also. But I didn't write things that way in large measure because the geometry, I mean, that's a necessity of the physics, but the symmetries in the geometry naturally are with the P1 cross P1 cross P1 for B3, and P1 cross P1 for B2, and simply project out the first coordinate. So for 90% of the talk, or maybe even 100% of the talk, if I don't get through what I planned, we're going to operate where this one is just P1 cross P1. This one is P1 cross P1 cross P1. projection just kills the first P1. And yeah, I'll have, if I wrote homogeneous coordinates here, I'd have like U naught, V naught, and then I'd have a U1, V1, and a U2, V2. And the involution is the UI, VI's go to the UI minus VI. That's all. And of course, you have to choose an S gut that's invariant under that involution. Okay, any other questions? Okay. So, first I'll write up the two sections upstairs. So we're going to work upstairs for a long time. We're not going to act by the involution for quite a while. So let's do our W4. So that's the Calabi-Yau fourfold. That lives in the projectivization of, let's see, what do I want? The vector bundle O of B3 plus OB3 of 4 plus OB3 of 6. This is, of course, rigged so that this hypersurface is going to be Calabi-Yau. And so these numbers are with respect to the smallest polarization of this thing, O1 cross O1 cross O1. That really should be have 3 coordinates to it, right? So if we call those 3 polarizations E1, E2, E3, this is 4E1 plus 4E2 plus 4E3, and then 6. Okay. And yeah, the coordinates I'll use here are the standard ones everybody uses. And if we set W equal to 1, the equation of the Calabi-Yau fourfold y squared, everybody who works with this is day 1, right? You have this x cubed plus a5 x y plus a4 x squared plus, whoops, sorry, forgot a z. Z x, what do I get? X squared plus a3 z squared y plus a2 z cubed x plus a naught z to the 5th. And what you're supposed to think about when you see that is the evolution of an E8 singularity, keeping an A4 singularity in sight, that is, in the whole way up. So now I've got to tell you what the bisection is. So tau, this simple thing, takes an element of B3 and sets it to, well, homogeneous coordinates. It would be W Z squared minus W Z cubed minus W Z cubed. So that's our other section. The section C says B3 to right, 0, 0. So how do we put those two sections on equal footing? Probably this is.
So is Z going to be your equation of S star?
Say again?
Is Z be your equation of S star?
No, yeah, it's probably it's the.
What is Z? What is Z?
What is? Oh yeah. What is Z? Sorry, forgot that. S gut is B3. Yeah, I didn't say that over here, did I? Is Z. So
This will be degree 222?
that's right. Yeah. So that, of course, this is a K3. Right? All right. So now, well, yeah, some of you probably already have done this in your heads, but it took me some weeks to figure out that this was the right way to do it. This is a duh. Elliptic curve, right? I could say this in fancy language, but I don't think in fancy language. So. Okay, elliptic curve. C is out here at infinity, right? Tau is over there. Well, what's the obvious thing we want to do? We want to take, if you will, minus tau over here. So I'll call this nu. So of course, if you have these, you've got the third point. And so what we want to do, of course, on each fiber in B3, we want to project from this third point. Is that right? In other words, in some sense, we're picking a linear series of degree 2 on our elliptic curve. Is that okay? So we project. And what that projection does, essentially, is it kills this, and the image of that projection is the projectivization of these two, which we can, of course, renormalize to O plus O of 2. So if I call this space up here P, what we have when we do this projection is we first have blown up P, right? Blown up the P2. And then we have a morphism down onto this Q. So this is a threefold. And it's the projectivization of O plus O of 2. And yeah. So, and this is an F1 bundle. Is this all right? Okay. So now, to maybe interest people for whom this was regarded in grade school or something, the advantage of this is there's there's something called the spectral variety that I'm going to say what it is in a minute, where all the action happens. And we are going to produce, in a very natural way, the spectral variety as sitting inside this cube. So when you look at the equation, what you see is that, so in here, we have what I'll call W4F, sitting up here. And this is a 2-to-1 branch cover. And so, obviously, what we do is write down the branch locus and use the geometry that we have a very simple object now, a 2-sheeted branch cover of something that we totally understand. So, let's see. Yeah. So let me do coordinates here. So we have W4 hat. It's got all of its coordinates. These coordinates down here on Q, there is capital X and capital Y. The relationship is capital X. See how do I do it? Yeah. Right in the right order. Capital X is equal to little x minus, right, z squared w. But capital Y, now, we're not projecting from this thing, we're projecting from this down here. Okay. And capital Y is y minus z. I'll have to define this in a second. Z plus A420 z squared w, where A420 is A4 plus A2 plus A0. I erased the equation, but the A's were the coefficients of the, and the condition that tau is a section is the condition A420 equals A53. And for those of you who worked in this business, A420 restricted to S gut is where the 415 bar representation occurs. Is this okay? So now, if we're careful, we could just replace this W4 bar by two-sheeted covering branched along this discriminant, that's all. So this will be my notation. this is contained in Q. This equals branch locus. Yeah, I guess I should give this back a name. Let's call this capital P. So the way that we're going to resolve the singularities, now we have a branch cover, right? So I can just, if, let's see, what did I call it? Its equation. I didn't call it anything. I have in my notes, I wrote it out. So just for the sake of truth of packaging, let me write it out. Oh, I wrote it out. And the point of this is going to be, we're going to be able to see all the singularities of this thing in very elementary terms now by just looking at the singularity of this branch locus, right? Because the last factor, the y squared, right, that's governed by whatever singularity you have down on Q, inside of Q. So again, you do a little work and you say, oh my goodness, delta intersect with capital X equals 0 is empty. So I could do an affine set of coordinates and not have to keep track of so much. So we're going to let theta equal capital Y over capital X. Right? So we've taken an affine parameter such that the branch locus is captured in the finite part of Q, right? Q is fibered over B3. And here is theta equals 0, and here is theta equals infinity, and in here somehow is my branch locus delta. It goes down here, but it doesn't reach there. There's just enough curvature to keep it away from infinity. Is that right? So now I want to write down the equation of my Calabi-Yau threefold and its branch locus in this standard double cover form. This is the one thing that I wish I would have a projector for. So if you want to get a drink of water or something. I meant to make a joke at the beginning because so I am on in years. And so every time before I give a talk, I always go to the restroom. It was getting to be 11:30, and the line at the restroom was incredibly long. So if I excuse myself for a minute, that will be why. Anyway, but you guys can, this is going to take a minute. Okay, so we've got some capital W squared equals, well, this is the double cover, and this side is going to be the equation for the branch locus. A5 theta plus A4 z squared minus 4 A5 A 4 2 0 z. I'm going to write this all out because what you're going to see is all the singularities of the branch locus just present themselves. So let's see. So we're writing this out, ordering terms by total degree in the two coordinates z and theta. So over S gut, there are singularities here. We've got quadratic terms. Okay? So then we've got degree 3 terms. Yeah, well, I'm not sure. Well, let me humor me. Let me do this minus 2A5 theta cubed minus 2A4 theta squared z plus 6A5 plus 4A420 theta z squared, don't have enough room on the blackboard, minus 2A4 plus 4A2 plus 4A5 z cubed. So that's the cubic code. And then there's one more level of this, which is controlling whether we could resolve the singularity with one small blow-up. That would be controlled by this last term. Plus theta to the 4th minus 6 theta squared z squared plus 8 theta z cubed minus 3 z to the 4th. All right? So this is the branch locus, this is the double cover, and since we are going to have to put the spectral variety, whatever that is, inside of the fourfold, we have a way of projecting it down to this threefold, or sorry, to the simpler fourfold, with whose vertical variable is theta. Okay, so over S gut, right? That means z equals 0. What have we got? So for me, most of this project has been doing high school algebra correctly, which usually I have to do it 4 times before I get it right. Anyway, if you do the algebra, okay, you're going to see it's theta squared times A5 minus theta squared equals 0. That's all there is. So this is pretty simple, right? You've got a double locus along theta equals 0. You got a square up here. And so the quadratic cone is non-degenerate except over these two matter curves. I'm sorry. Yeah, except over these two matter curves. So you just do a projectivize the pair theta z, and that resolves the singularity over this, over the theta z equals theta 0, except over here. So you'll just get a two-parameter family of ordinary nodes, right? Surface nodes. So just canonical resolution of each one, just put a P1 in, you're done. Over here, then the second degree term is a perfect square. So the quadratic cone is of rank 1 in the normal direction, right? The quadratic cone is a 2 by 2 matrix over the base. So it's a rank 1, where this is 0, but if this is, if the cubic cone is not 0, then you're resolving the cusp singularity, 2, 2, 3, x squared plus y squared plus z cubed. And that has a pretty simple resolution also. It's just it's got two P1s as the exceptional locus rather than one. So, yeah. Let's see. I said that wrong. Cusp. Blow up. Right? That resolves the cusp, but we have the exceptional locus tangent. So we resolve the singularity of the branch locus, so the double cover is going to be smooth, but the exceptional locus becomes reducible upstairs. We get two P1s. That's okay. Anyway, yeah, I'm getting short on time, so let me go to where do the I'm going to have to just say this. So this was where we wrote the blow-ups and everything and examined the singularities along the zeros of theta. On the other board, if I had a ton of time, I'd put the analogous breakout in terms of z and a5 minus theta. Same story, right? But the only difference is that there, the quadratic cone is always rank 1. So what does that mean? That means when we did this projection, we have two components over, so this is what? This is two components. This is in the W, I need a new name for this. This is W4 upper 1. one component is the original cubic curve, just desingularized. In the case it was singular. Well, I've said this wrong. I'm only going to talk about the geometry of this over Sgun. So there, I'm going to call D0 the projection of the original singular cubic over points of Sgun. It's an A5 singularity, right? The exceptional locus, call that D2. When I resolve this singular locus on the branch locus, I get a new component that meets both of these. That's, I'm going to call D1. When I resolve this one, since the quadratic normal cone is rank 1, the inverse image upstairs becomes reducible. So that's going to give me, so over here I blew up theta equals 0. That gives me D1. Over here I blow up A5 minus theta equals 0. That gives me D3 and D4. And over here, I have some singular locus, just the curves of singularities, but it's cuspadal, not ordinary double points. So that means when I resolve, I have two P1s, one that goes in the D3 and one that goes in the D4, and they, of course, get interchanged under, if we interchange D3 and D4. So, moral of story is what we have is the extended Deacon diagram of A4. What we have is flat SU5 connection given by that, just moving, following the components over Sgun. The Wilson line, that is the Z2 action, will break that S5 symmetry down to S3 cross S2 cross U1 symmetry of standard model. So that's sort of what the geometry is giving you about the physics in one sense. And in the last 2 minutes, let me say something about the spectral drive. Because this allows you to very easily compute G flux, D term, and give the right answers for how many quarks and leptons there are and stuff like that. So if you look at where these singularities are, yeah, I'm just going to write this down. We started with an original equation that had A5 xy plus, leave out the, for reasons I don't have time for, the y squared and the x cubed. We just set this equal to 0. A4 x squared z, etc. Now, if you want to find the singular loci in here and where the explosions take place, you say, I'm going to use a coordinate t, and t is little y over little x. And then you substitute it here, and you get the following homogeneous form of degree 5. A5 t to, well, I'm really going to. You get something that factors. And let me just write down what that is in 1 minute here. Well, yeah, I'm not going to make it. So substitute t for y over x, and you get A5. You get one factor, which is where our section was. You get another factor, which is A5 t to the fourth plus A4 minus A5 t cubed z plus, etc. Over there we have a theta. Back here we have a t. And you do some algebra, and you see that that theta is A420 over 1 minus t squared. T tilde squared. Let's see. No, I'm lying. This is, there is a z here. We've got to rescale as we get there. So then that means, since you know the equation of the spectral variety over here, I can get the spectral variety inside of this cube. Turns out it lives entirely on one of the two sheets of that. And so that's what, yeah, I'm going to have to stop because I'm out of time. Anyway, thank you very much.
Any questions?
So how does this relate to G-flux?
So, I mean, what you need for the G-flux, right, is the image that you need to control, like the self-intersection of the image of the Higgs, that is of this spectral, I think I'm calling it.
So you're putting the G-flux on the surface?
Right, that's, yeah, I mean, so the G-flux is created over here in little z, little t coordinates, right? This relationship helps it, it's got an equation over here, got a double cover, control its branch locus. It's really easy, that's all.
Other questions?